Like I said, that is going to be the focus today. We're going to work on graphical lasso. I We were left with some illustrative examples in the last material. We're going to continue from that today, and I'm also going to walk you through the implementation of graphical lasso in R. Okay, so we're going to start with the simulations. Of course, we want to simulate data set from Endo's range graph, and we want it to have a probability. There's an edge between node that is 0.1, which we can call a weaker relationship. Um, we actually want to vary sample size. We look at the combination of a small sample and large sample. For instance, when sample size is 50 and the numbers of features is 100. And when sample size is 150, the numbers of features is 100, which means we want to consider a situation where the numbers of features is less than n and the numbers of features is greater than n. And when we do the simulation, we actually want to run that over 20 repetitions. Okay, we don't just want to have just one repetition. Okay, we want to have 20 repetitions so that we're going to find the average, okay, of recall on the standard deviation. And before, we have to make sure the data set is standardized before implementing LASSO. Okay, now I needed to pay attention to what I'm trying to show you now. If we assume that the true precision matrix is this guy, okay, let's say that is the truth. That's a true precision matrix. And we actually want to use model selection criteria, don't forget, to identify what would be the appropriate values of lambda. Don't forget, the lambda is regularization in the lasso component of the graphical lasso model. If we use if we use cross validation, I needed to compare the cross validation with the true precision matrix. You're actually going to see that the cross validation does not exactly match. Do you see what I'm saying, right? Okay, like here now, this is having just one here in the true precision, but here it is 1, 2. You see the difference, right? So which means the cross validation as a technique of selecting the appropriate regularization parameter may miss some relationship. Okay, now if you want to go by way of a BIC, okay, I need to pay attention to this now. Okay, you're actually going to see that the BIC and the CV here agree, right? Look at that. The BIC and the cross-validation agree. But if you take a look at the extended BIC, in the extended BIC, we have incorporated um, the the regularization penalty. Okay, if you compare that with the true precision matrix, you're actually going to see that the extended BIC matches that closely. Can you see that, right? Okay, and that is why at times we prefer using extended BIC. Extended BIC, we penalize complex relationship in favor of sparser, relationship. Okay, so this is when you want to go by way of graph. Okay, if you take a look at this is the precision matrix. Okay, you can try to see the one that is very closely that match that. But let me show you this. I want to compare three things across three module selection. TPR is talking about true positive rate. True positive rate. FPR is false positive rate. And TDR is true discovery rate. We want to compare the TPR, the true positive rate of cross-validation, BIC, and the extended BIC. The values that are not in the parentheses is the means of how many. This is what we did for 150 observations and P numbers of 100 features, and we have 20 repetitions, and we average, recall, okay, if you take a look at this now, with 0.71, all of that, they are the mean, okay, they are the means. The one in the parentheses are the standard deviations. Okay. Now, if you take a look at, if you want to focus on this guy now, when I say true positive rate, you actually want to talk about the proportion of time, okay, the model was able to identify true relationship. Maybe the relationship are true, and he was able to identify, so the proportion of time identified two relationships, you see 0.71 on average across 20 simulation, 20 repetition, 0.71 is the recall. Okay, if you compare the BIC with the EBIC, you're going to see that the extended BIC has the highest rate of recall, 0.99, followed by BIC 0.98. The worst here is a cross-validation. The cross-validation has a lower recall. Does that make sense to everyone? Because the highest value here is being favored. When it comes to true positive rate, the highest value is what we're going to favor. Does that make sense to everyone? True positive rate means true relationship. Okay, 99% of the time. Okay, the extended BIC actually have a recall for true positive rate. Now, for false, okay, for false positive rate, when we talk about false positive, okay, we will actually want to see what is the proportion of time the model was incorrectly identify relationship that should not be true. That relationship should be spurious, but it identified it to be a real relationship. So which means here we are looking for lower number. The lowest number is going to be the good number. Does that make sense? But if you take a look at all the model selection criteria, they perform greatly, because if you look at the number 0.0001, they have a very small, they have a negligible number across. Do you see that, right? The performance is the same when it comes to false positive rates. Does that make sense? But when it comes to true discovery rate, we need an higher value. True discovery rate. What do we mean by true discovery rate? True discovery rate means no relationship, it did not identify that. Relationship exists, it identified that. We are counting the numbers. The highest number here is actually going to be favored. And which one has the highest number here is the cross validation. Okay? If you look at the cross validation, 0.97, that's the highest recall. So which means, the choice of model selection criteria actually depends on what you want. It depends on your intention. Are you interested in true discovery rate? If your focus is on true discovery rate, then use cross-validation to determine the lambda. If your focus is true positive rate, then use extended BIC. I'm gonna take a look at this. See that? And if your intention is on false positive rate, you can use any of them because they all have negligible uh, values for false positive rate. Does that make sense to everyone? That makes sense to everyone, right? Okay. Now I'm going to go to another data set. This time around, it's a flow cytometry data. And this was actually, we want to borrow this from Easton et al., 2009. Okay, this very data set contains 11 proteins on 7,466 cells. Now, these are the protein variables. Okay, these are the protein variables. Each of the protein variable has 7,466 cells. Now, we have a summary statistics for each of the protein. We calculate the mean, the standard deviation, the minimum, and the maximum. These are just descriptive statistics, okay? But we believe that there's going to be interrelationship among these proteins that will necessitate us trying to obtain a precision matrix. And if we want a very good precision matrix, we actually want to use the idea of a graphical lasso, right? Because when you obtain precision matrix from graphical lasso model, we believe you're actually going to have a very stable covariance matrix. Okay, now we know what we're going to do. The problem we normally find ourselves is what is actually the regularization parameter that work. What is a regularization parameter that work? Like what values of lambda? Then I need to take a look at this now. Okay, so now we realize that we use a model selection criteria CV cross-validation and extended BIC. And this is showing the result for lambda equal to 0.01 for two of them. And you can see there is interconnectivity among the proteins. Okay, the interconnectivity among there's something I actually wanted to see in the cross validation. It is highly dense compared to extended BIC. The extended BIC we actually only go for what I call a sparser model. Okay, I just wanted to take note of that. Now, I want to go into another example. This time around stock return volatility data. And this data actually come from Demera et al., 2018. We want to be able to know where author estimate the global bank network connectedness. Let me tell you this, banks interact locally. When you look at the stock returns volatility, and banks also interact globally. Okay, so what we want to show you now, we actually select only economies where the number of banks in each economy is greater than 4 and a total of 54 banks. Okay, and we visualize the result. We exploit a multi-dimensional scaling algorithm. Okay, developed by ASCII 2009 to calculate the proximity between variables. You remember when it comes to proximity, when it comes to the distance, okay, when we have data set in high dimensional space and we want to project that into low dimensional space, we normally use the idea of MDS. I need to show this right now. I have Australia. When you look at the colors, I got Australia, Canada, China, Great Britain, Italy, Japan, and United States. Now, when you take a look at this particular picture now, okay, this visualizes network, okay, of uh, uh, stock return volatility for banks across countries. Stock returns volatility for banks across countries. Okay, we are considering Australia, Canada, China, Great Britain, Italy, Japan, and United States. And when you take a look at the node are the banks. Okay. Now the node at the bank, this is actually showing us interaction occur between banks in the United States, between banks in Canada, and not only that, there is interconnectivity, okay, between banks globally. Okay, because you know, there's something that we call some banks share cross-border relationship, okay, due to global market dependencies. Okay, now what I can see here is that banks within United States have very strong very, very strong intra relationship when it comes to stock returns volatility. Now take a look at this color now. Okay, you're actually going to see there's a lot of connectivity among those colors. The United States banks, can you see that? They cluster. Can you see that? They cluster. That's a domestic clustering. Okay. And do you know that there's also a cross-border relationship between United States Bank, the Great Britain, and Canada? Okay. I need you to look at that in the picture. Look at that. Okay. Can you see what I'm indicating in the picture? Okay. For Great Britain, the Canada, okay, there's a strong, there's a kind of border cross-border relationship among these banks. Okay. And when you take a look at Japan, I need you to take a look at Japan right now. Japan. Okay. If you take a look at Japan, okay, the Japan banks have fewer connection to bank outside Japan. I just need you to look at the picture. You see the color for Japan, right? It's like their banks are kind of isolated. Even, most of their banks. I just wanted to take a look at that. So this picture is a network for stock return volatility where it enables us to see, uh, relationship uh, between banks locally and relationship between banks globally. And this is the reason why I don't pray for war. I don't like war at all. The reason why I don't pray for war, because what happened in a country has a tendency of affecting another country. Let me tell you something. This country is beautiful, okay? But something pushed me to this country. Something pushed me and my family to United States. On a normal ground, home is sweet. I just want you to know that. Home is very, very sweet. But when you have crisis at home, I pray that we shouldn't have crisis. It's not easy at all. You have crisis at home, as human being, you want to survive. And that is the reason why what we should be looking for is, let there be peace anywhere in the world. Imagine we wake up one day, there's no crisis. There's nothing like sorrow. I don't know how it's going to happen, but it can happen. And that will depend on understanding. So relationship exists. And that's why when something happens in other countries, it affects what happens in another country too. And that's why can't we work together to be able to do something that is common to us? Okay, now these are possible feature or future feature that, there are so many topics when it comes to graphical lasso. The one I've presented in this class, the graphical lasso is for continuous variable, right? And that was why we are zooming Gaussian distribution. Does that make sense? we also have a graphical lasso for discrete data. Okay, we're not doing that in this class. And that was actually developed by Lowe and Wainwright in 2012. Then we also have a joint graphical lasso. We have a time series graphical lasso, and we also have a time varying graphical lasso. So graphical lasso has a lot of variants, but the one we focus on in this class is when the random variable is continuous. Now, I want to take you into R. My TA is going to walk you through this in R. I'm actually going to tell my TA today that the lab for next week, it shouldn't meet in person because it's Thanksgiving week. I'm going to tell my TA to record the lab and share with the students. I'm also going to tell my TAs for Start 3011 and TA for this class that I should record the lab for next week and share with the student. There's not going to be in-person lab section for next week. Now, let me tell you this. I'm only going to have an in-person class with you on Monday, but on Wednesday, I'm going to have you join my Zoom. You can be anywhere in the world. The lecture on Wednesday will be conducted on Zoom. Automatically, there's no lecture on Friday. Okay? But I want you to enjoy your Thanksgiving uh, season. Okay, so how do you choose lambda? Through cross-validation. Okay, I walk you through, I show you the formula on Wednesday, but how do you do that in R? Don't forget, what you want to estimate is precision matrix. That is what you want to estimate. Now I need you to take a look at this code. This is choosing lambda through k-fold cross-validation. Okay, you are required to load a package called GLASSO. Okay, you need to install that. And these are the code. This is the code right here. You see the code right here? You can see train, test, and so on like that. It continue. Look at that. You see log, log, the theta. You remember that is part of the formula. Okay, that is what we coded. Okay, okay. This is a general code. Okay, for cross validation. If you want to figure out lambda, but let me be specific with my example now. Let's say, for instance, the number of observation is much greater than P. You know what I mean? When the number of observation is far more than the numbers of features, what will happen? There's no serious problem. The covariance matrix will be invertible. You know that, right? The covariance matrix will be invertible, right? Okay. Now, let's say I still want to use a graphical lasso and I want to use method of cross-validation to figure out what my lambda is going to be. I needed to pay attention. You set a seed. Okay, set a seed. What am I using here? I'm using an iris data. Can somebody tell me? Where am I saying -5? Can somebody tell me? For extra credit. Why -5 in iris data? Oh, someone said something? The last column. What do you think last column it is? Eh? Oh, the label. Is it the label? Exactly. We want it. Is that what you also want to say? What do you want to say? Yeah. So I was asking why -5. Okay. So why -5? You send me a message for extra credit. Okay. Now why -5? The same as what he said. I just wanted to say it. And should be excluded. That's all it means. Because we only want to focus on what? On supervised learning. Unsupervised. Does that make sense? Okay. Now You remember cross validation? I said they're going to be k numbers of code, right? Here I'm choosing 10, right? Now, what do you want to figure out? What values of lambda that work, right? You can have you can assume some values, okay? Now, the code continue, okay? At the end of the day, this is what came out. What do you see in the y in the s-axis? In the y-axis is the log likelihood. In the s-axis is the lambda, and you know the lambda that work. You look at the lambda that have the maximum log likelihood. Does that make sense? If you trace it down, whatever lambda, whatever the value of the lambda, that is it by cross validation. That's exactly what we mean. Okay. Now, what if in a situation where the number of observation is less than p? Okay. The number of observation is less than p. Okay. You know, a situation where the number of observation is less than p, your matrix, the covariance matrix will not be invertible. Does that mean saying inverse will not exist? Okay. Now you do the same, we actually follow that same code, and at the end of the day, look at what we have. This is what we have. Where is the lambda point? Is this guy here? Do you see that guy? Then you project it down. That is it. You look at the height. You know, we're talking about log likelihood, you're talking about the maximum. We're looking for the values of lambda that will give us the largest log likelihood value. And that values of the lambda will be the one that is optimal for the shrinkage. Does that make sense to everyone? This is how we do it. This is how. So if you have any financial data, or if you have maybe you're working with a gene sequencing and you have so many genes, and you actually believe that genes are interrelated, okay, and you want to construct a precision matrix situation where the number of observation is actually less than the numbers of features, you may not be able to obtain inverse of a covariance matrix because of the fact that the determinant is going to be zero, singular. A singular matrix, the inverse of a singular matrix does not exist. And the way to do that is to go by way of a graphical lasso, okay? By way of graphical lasso, because the interconnectivity among features, is dense, and there's possibility some relationship as spurious, and introducing lasso is to shrink, although it's a weaker relationship to zero. Okay, don't forget, we benefited from the conditionally independent in the graphical model. You remember when two variables are conditionally independent, then it means in the precision matrix, they will have zero entry, because they are conditionally independent, given the rest. Okay, so this is our intention with graphical lasso. Let me tell you this. The graphical lasso that we did here is only for situation where the random variables are continuous. And when they are continuous, they are assumed to follow Gaussian distribution. Of course, Gaussian normal distribution, they are distribution for continuous random variable. Other graphical lasso exists. Okay, we got graphical lasso for discrete random variable. We didn't do that in this class. Okay, we also got a joint graphical lasso. And not only that, we also have a time series graphical lasso. We also have a time varying graphical lasso. Okay, the reason why we're going to have a time varying graphical lasso, has anybody offer a time series course in statistics? Time series? Time series. Oh, okay. Okay, there's a lot of work going on in time series when you want to talk about time varying volatility put forward by Eagle in 1982. that they call GAC, Generalized Autoregressive Conditioning Heteroscedastic Model. So there's a lot of work going on. Statistics in general is very, very attractive, very, very lucrative. All we just need to do is spend your time and explore. There's a lot to explore in statistics. Okay, so today, I think I've been able to walk you through some examples and of graphical lasso using financial data or the way to protein data. And of course, I demonstrated the use of module selection criteria, selecting the lambda, which is the regularization parameter, because um, the if you sparsing a module depends on the choice of lambda. We don't choose lambda arbitrarily. Don't forget, lambda goes from zero to one. Okay, we don't just choose 0.1 or 0.2. We don't choose that arbitrarily. Okay, we got module selection criteria, and we got more than one module selection criteria. You're going to be wondering, why do we need to have more than one module selection criteria? Is the same reason why we need to have more than one court. Do you know I can get maybe if I don't get justice in one court, I can decide to go to an upper court. And whatever decision, if they did not treat my case fairly in a lower court, then the upper court can give me justice. Okay, we also have more than one selection criteria because each of the selection criteria has limitation. Okay, one thing that I know extended BIC does, the extended BIC will penalize, it's very good to prevent overfeeding. Overfeeding. Okay, we don't want a situation whereby your model will perform or your algorithm will perform good on training data, but will perform poorly on test data. When I say test data, I mean on seen data. Situation whereby a model performs great on training data and doesn't perform great on unseen data, okay, is because that model has captured noise. I'm going to say that again. Because it is expected that the model should only capture signal. When model capture both signal and noise, there's going to be an issue. So situation whereby the numbers of features is very close to the numbers of observations, or the numbers of features is more than the number of observations, then whatever sample covariance that you're actually going to compute will be noisy. Okay? It means it will capture noise. And capturing noise means it will report some relationship that are spurious. Okay? And that is the reason why the knowledge of graphical lasso is going to come in. Okay, there are two things to benefit from in graphical lasso. The graphical model itself we use, we're going to benefit from the idea of a conditionally independent relationship situation with asset returns. If our asset returns, if the return from asset have a weaker relationship, okay, using the idea of a graphical model, okay, that will be deemed to be called, conditionally independent, given the other returns. Okay, and of course, conditionally independent, what is going to happen? The lasso is coming in as a penalty now to shrink the coefficient, okay, that relationship to zero. And shrinking that to zero is actually bringing in sparsity into the model. What is a sparsing? It's actually sparsing. Sparsing means is remove spurious relationship that could make the network to be noisy. We don't want the network to be noisy. And that's what we're trying to do. Go ahead. Okay. It depends. This is what happened. I think I showed you this the other time. Uh, Based on the simulation study, the only way to know is through simulation study. And through simulation study, uh, you're going to have more than one repetition. Okay. You can take a position for a particular dimension. Now take a look at what I'm trying to show you here. Okay. Do you know, if I really want to know which one is appropriate between cross validation, the conventional BIC, and the extended BIC. If I want to prioritize through positive rates, I will go for extended BIC. Do you see the board? Why am I going for extended BIC? Because it has high rate of recall, 0.99. Does that make sense? Oh, what situation? Oh, it depends on the researcher. You know, that's a good question because true positive rate means okay, if I'm interested in a let me just in a true relationship, let's say for instance, in the real life, true relationship exists between these two variables, and I want to know which one because I'm going to tell you this. Model is not the same as reality. We're using model to depict reality. There's always going to be a gap, right? Now, the question is, if true relationship exists, the model cannot identify all the true relationship exactly. So the true positive rate is now trying to say, out of this criteria, which one we identify more if it exists? Then we're now trying to say, as we extended BIZ, 99%, if 100% true relationship exists, it will identify 99%. So if the researcher is interested in identify true relationship, okay, then it will actually go for EBIC. So whether to choose true or positive relationship or false positive relationship or true discovery rate, it depends on the researcher. Does that make sense? It depends on what you want. But on average, it is better you report the three. So that you're going to say, if I want to make my decision here, I'm going to say, based on true positive rate, I will go with the extended BIC. Based on false positive rate, what do we mean by false positive rate? Naturally, no relationship, okay? But the model say there is. That's a spurious. That is what make the model to be noisy. Does that make sense? That is the noisy aspect. And which criteria will actually lead to small false positive rate. If I want to base, it is not all the time. If I want to base on this data set, okay, in terms of false positive rate, they are all the same. It's very, very small. Look at that. The second one. It means I can go with any of the criteria. But the last one is true discovery rate. Let me tell you this. If I happen to be the researcher, you know what I'm going to choose? What I'm going to go for? It is true discovery rate. Because you know what they call true discovery rate? The true discovery rate is going to say, okay, when true relationship exists, I identify some numbers, a great number. When true relationship does not exist, it does not identify. And that's why if I want to choose out of the three, whether true positive rate, false positive rate, true discovery rate, I will go for true discovery rate. But it is better you report all of that. When you are working with classification problem, maybe a question that has to do with customers in a bank apply for a loan and you want to classify new customers that apply for a loan on whether they're going to default or not. Okay, that's a supervised learning. Okay. Now, if we want to do that, at the end of the day, when we finish with the classification, we compute a lot. We talk about recall. We talk about F1 score. There's so many uh, metrics of evaluation that we normally report. Because what a particular set of researcher prefer may not be what the other set of researcher prefer. And that is the reason why, to be on the safer side, why can't we compute all of that? Does that make sense? So if I want to go with, so which means with a true discovery rate based on this that I said, I'm going to go with the cross validation or go with the extended BIC, because when you see it's, it's telling you this is worse. BIC, conventional BIC is worse for these are 83%. But look at the other one, 0.97, 0.95. I can go with either CV or extended BIC. Is there any question on that? Go ahead. Okay. You know, probability, let me answer your question by saying probability and proportion are the same. If I say 0.7, which is a proportion, right? It's also a probability because they all go from 0 to 1. So when we say recall now, is 0.71 that you are seeing, they are more or less like 71% recall, 97% recall. Okay. Now, I want to ask this question. Is there any of these that have 100% recall? It's not going to be possible. And that confirms what Judge Boss said. Judge Boss said all models are wrong, but some are useful. And he said, when you ask a question whether a model is true, if you mean complete true, then a model is not true. Because a model cannot give us exact characterization of reality. You know, I received a bad news I think some month ago. Uh, my PhD supervisor died in Nigeria. You know, he was traveling from one state to another in Nigeria. Now, this PhD supervisor that supervised my PhD in 2000 and between 2012 and 2016, actually, uh, he was a very good model forecaster. Like he has used statistical models to forecast the future. But you know what? He was not able to predict that he would die the same day he died. And that is to tell you that model can never give us exact characterization. There's room for surprises. And that's why we need to take things easy. So whatever we get, okay, they are giving us approximate reality. Approximate reality. There is no algorithm, there's no model that will give uh, exact characterization of reality. May the soul of my professor rest in perfect peace. So that is that. I'll stop there. Make sure you all stay safe and have a lovely day. Bye for now.